So today we are going to be solving Cambridge IGCSE Chemistry Paper 2 Multiple Choice Extended October-November 2024 Paper 22. So let's get started with this paper. The first question says, oxygen melts at a negative 219 degrees Celsius and boils at a negative 183 degrees Celsius. At which temperature is oxygen a liquid? I guess to solve questions like these, the first important step should be to make a line on which we can represent temperatures. Okay, over here we have negative 219, over here we have negative 183, and over here we have temperatures that are higher. For instance, I can say we have negative 160. So that's how negative temperatures work. You got to understand, the higher the number, the lower the temperature. Okay, negative 219 is a smaller number than negative 183, because the negative numbers, the bigger the number, the smaller its value or worth. Okay, so now we have to place when it's solid and when it's liquid. Over here right now, this is the melting point. This means before this line it is solid. Over here, between this melting and boiling point, it is a liquid. And after this boiling point, it's going to turn into a gas for sure. Okay, now let's read each option carefully. At which temperature is it a liquid? So we need a temperature that's between negative 219 and negative 183. Okay, first temperature is negative 225. Okay, negative 225 is a bigger number than negative 219. So instead of coming ahead of negative 219, it's going to come back. It's going to come somewhere over here. So let's place it. It's going to be somewhere over here, and negative 225, but at this it's going to be a solid. Negative 189. Okay, negative 189 is a bigger number, so it will come over here. Negative 189. Over here it's going to be a liquid. Then we have negative 175. It's going to be ahead of negative 183. Over here it's going to be a gas. Negative 175. It's going to be a gas, and 25, obviously it's going to be a gas. So the only temperature at which it's liquid is option number B, because it is between negative 219 and negative 183. That was the major concept in this question. Moving on, the pressure of a sample of a gas is decreased, the temperature is kept constant. Okay, now one thing you have to understand, that whenever the temperature is kept constant, that means the kinetic energy of the particles is constant. That means the speed of the particles remains same. So this word over here is very important, that the temperature kept constant, meaning the particles won't gain or lose speed. Which row describes the effects on the particles? Okay, movement of particles, it's going to be slower or no change in speed. Always remember that whenever you are keeping the temperature constant, there's going to be no change in your speed. Okay, now there's no change in the speed, but still the pressure of the sample has decreased. That means you should always remember that the pressure of a gas is because of the collisions. Because of the collisions, there is pressure. When two particles collide, not with each other but with the walls of the container, they exert a pressure on the walls, and that's why your gas has a pressure. So if the pressure is getting decreased, that means the number of collisions are getting decreased. So the collisions between particles, they're gonna occur less often, hence making option C the correct one. Moving on to the next question, which says rubidium has two isotopes, Rb85 and Rb87. Okay, which statement explains why both isotopes have the same chemical properties? Always remember that isotopes have a different neutron number, but their proton number remains same, and the chemical properties of an element is always determined by one thing, and that is the number of electrons. Your electron number determines your chemical properties. If two things have similar chemical properties, this means they have same number of electrons, or the electronic configuration. They have the same number of protons. Protons don't make the chemical properties. They have the same electronic configuration. That's going to be the correct answer. Moving on, which pair of elements react to form a compound with a strong attraction between oppositely charged ions? Okay, we need a pair of elements that react to form a compound with strong attraction between oppositely charged ions. I guess simply by reading the statement, by looking at the word that I need oppositely charged ions, I get to know that what the question is talking about is a ionic compound. So to make an ionic compound, I simply need sodium and oxygen. Sodium is going to form sodium ions, which are going to be Na+. Oxygen is going to form oxide ions, which is Na not Na, O2 negative, and that's going to form Na2O, which is going to be sodium oxide, and there's going to be attraction, electrostatic forces of attraction between sodium and oxide ions, and since they're this is positively charged, this is negatively charged, they're oppositely charged, so we are fulfilling all the statements. All the rest, either they are both metals or they're both non-metals. Okay. Question number 5, it says 4 substances P, Q, R, S are described. P is diatomic. Okay. Let's just highlight the important stuff that P is going to be diatomic. Diatomic simply means it's going to exist as two atoms that are covalently bonded to form a molecule. For example, Cl2. This 2 tells us it's diatomic. For example, O2. For example, H2. All this tells us that these are diatomic. Okay. Q is a good conductor of electricity when solid and when molten. Okay, it's a good conductor when it's solid and also when molten. This tells us that it's likely to be a metal, because metals are good conductors in solid state. It cannot be an ionic compound because ionic compound don't conduct in solid state. Okay, R is silver solid with a very high melting point. This tells us that because it's a solid and very high melting point, that tells us it's likely to be a transition element or transition metal. S reacts with oxygen to form a brown gas. I guess they're talking about nitrogen dioxide, NO2. So S can be my nitrogen, because nitrogen dioxide is a brown gas. Which substances are metals? Okay. For example, the first thing I'd like to tell you guys is metals cannot be diatomic. So first thing that we do is we cross option this and this one, because nitrogen is also not in metal. The two metals that we found are Q and R. So Q and R, it's going to be option C, because Q is a good conductor. We know metals are a good conductor, and R is a silver solid with high melting point. And metals have high melting point, especially the transition elements. Okay. Which diagram shows the covalent bonding in a molecule of carbon dioxide? I guess that's what we know, that oxygen forms two bonds. So over here, there's a single bond of oxygen. That's wrong. Over here, both bonds of oxygen are single cross, and over here, oxygen is forming a triple bond. That's incorrect. So this is correct, that oxygen forming two bonds and carbon in total forming 4 bonds, because carbon has a valency of 4. That means that in its last shell it is 4, and it need 4 more to get a full shell. And oxygen has a 6 electrons in its last shell. That means it just needs 2 more to get 8. That's why it forms 2 bonds. Moving on to the next question, which says that the bonding, structure and melting point of sodium chloride and sulfur dichloride are shown. Over here, we know that sodium chloride is an ionic compound and sulfur dichloride, because sulfur is a non-metal. That's what I know for sure. And I know chlorine is also a non-metal. And I know that non-metals bond together forming covalent bonds. So one important thing that I know over here is that my sodium chloride for sure going to have high melting and boiling point because it's ionic, and sulfur dichloride is going to be covalent, having a low melting and boiling point. It has a giant lattice. It is a simple molecule. That's what we know. Okay, why does sulfur dichloride have a lower melting point than sodium chloride? Okay, we are given with a table. We're given with a bunch of information, and now we have to conclude that why does this sulfur dichloride has a lower melting point than sodium chloride. Okay, now I'm going to explain you guys one thing, and if you guys get this thing, I guess that's going to save you a lot of marks. Okay. Now try to understand the thing that I'm going to explain. Over here, you have sulfur dichloride. Sulfur dichloride simply means you have a sulfur atom, and with that, you have 2 chlorines atom. Dichloride means 2 chlorines. Okay, so that's it. But now, you need to understand one important thing. You have a lot of sulfur dichloride in a, for example, in a sample of sulfur dichloride, you're going to have a lot of sulfur dichlorides like this. So, you have a bunch of sulfur dichloride. And this is a simple molecular substance. That means it is going to have a low melting and boiling point. But why? The reason for that's very simple. You see this sample of sulfur dichloride having a bunch of sulfur dichloride molecules. Now the thing you need to understand over here is that between these two molecules, this is one molecule and this is the second molecule. Okay, this is one molecule, this is the second molecule. Between these two molecules, there is a force of attraction that is holding the two molecules together. Okay, in a sample, there is a force of attraction that's holding the two molecules together, and that force is very weak. So we give it the name of weak intermolecular forces of attraction, or weak IMF. Okay, so there is weak IMF between these two molecules. And always remember, whenever you are melting a simple molecular substance or boiling a simple molecular substance, what you're doing is not breaking this covalent bond. Okay, now with green I'm highlighting the covalent bond. Basically, this one right here is your covalent bond. This is your covalent bond between sulfur and chlorine. And with yellow, I'm highlighting the intermolecular forces. This yellow between the two molecules is the intermolecular forces. Remember that this covalent bond is very strong and you cannot break it with a low melting and boiling point. The thing that you always break in simple molecular substance is this force of attraction between the two molecules, not this covalent bond. In simple molecular substance, you don't break the covalent bond. What you break is this force of attraction. That's why it has a low melting and boiling point, because you are just melting all these weak IMFs between the molecules, between these two, between these two, between these two. They're all weak. That's what you're breaking. Okay, so that was a very important concept I guess most people struggle with. They think that you're trying to break the covalent bonds. The covalent bonds are very strong, so you cannot just break them. What you're breaking is this thing. Okay, I hope that was clear. Moving on, why does sulfur dichloride? Because the covalent bonds in sulfur dichloride are weaker. What do you guys think? What I just explained. Are covalent bonds weaker? Covalent bonds are extremely strong and you cannot break them. Moving on to next statement. The covalent bonds in sulfur dichloride are weaker. No, you don't break the covalent bonds. That is what the examiner is trying to test. Does the child know that are they breaking the covalent bonds? These are the covalent bonds, or are they breaking these intermolecular forces? So that's the thing, the attractive forces between the molecules. So that's the attractive forces is what we are calling the intermolecular forces between two molecules. In sulfur dichloride are weaker than the attractive forces between the molecules in sodium chloride. Okay, this part of the statement is correct that the attractive forces between molecules in sulfur dichloride are weaker. But the second part, which states that molecules of sodium chloride, what do you guys think? Sodium chloride, it's an ionic compound, it's an ionic substance, it cannot have molecules. This word is extremely misleading or misguiding, because I'm sure many children would have fallen into this trap. But sulfur dichloride, sodium chloride cannot form a molecule. It is an ionic compound with sodium and chloride atoms that are attracted towards each other because of their opposite charges. These are oppositely charged. That's why they both attract each other and they form a giant lattice. So that's what you need to understand. Okay, now option D, which says the attractive forces between the molecules in sulfur dichloride are weaker and the ionic bonds. That was what we were looking for. Over here it was molecules, that was incorrect, and the ionic bonds in sodium chloride. That's correct, because whenever we are melting a ionic compound, what we are breaking is the ionic bonds. Over here we are breaking the ionic bonds, but when we are melting sulfur dichloride, we are not breaking the covalent bonds. What we are breaking are forces of attraction, or the intermolecular forces. I hope you understand this concept right here. So we're done with this MCQ. It was a bit tricky, which required some concepts, but moving on to the next one. Diamond and graphite have giant covalent structures of carbon atoms. Okay, now you might think one thing that I just told you, that when we are dealing with simple molecular substances, what we break is not the covalent bonds, what we break is the intermolecular forces of attraction. Now you might wonder that carbon, the allotropes of carbon, which include diamond and graphite, they have extremely high melting point. Why is that? Because in diamond you don't have any intermolecular forces of attraction. In diamond, each carbon atom, this is one carbon atom, is connected to other carbon atom by covalent bonds. 1, 2, 3, 4. All carbon atoms are connected to each other by covalent bonds. So in diamond and graphite, you're breaking the covalent bonds. Okay, in diamond, graphite, and all giant covalent substances that have high melting and boiling points, you're breaking the covalent bonds. But over here, you are not. In simple molecular substances, you have low melting and boiling points because you cannot break this covalent bond. What you break is the forces of attraction. Okay, which statement describes graphite? Okay, now you might think one other thing. I know what is it. Graphite, right here, this is a hexagonal ring of graphite. Though my drawing is not very, good, but still, I guess it's somewhere similar to this. These are the hexagonal rings which graphite is made up of. And what basically happens between the layers of graphite is, look, these are two layers of graphite, and between the layers of graphite, you have these intermolecular forces of attraction. And you might think that because graphite has these weak intermolecular forces of attraction, you may be able to melt graphite with a low melting point. But whenever you're melting graphite, you are not basically concerned about these. You need to break the covalent bonds to melt graphite, because if you just break these, what's happened, the layers are going to slip over each other. They're still going to remain solid. You're going to form two solid sheets of graphite. Your pencil, the pencil with which you write on paper, that's made up of graphite. And when you are writing, basically a layer of graphite from that pencil, it basically sticks to your paper because it's a good lubricant. It can slip and slide, and that's why your pencils are so smooth. This pencil, the electrical pencil, is not, but the manual pencil with which you write on paper consists of graphite, and that's how the layers get slided, but it does not melt. So to melt graphite, you need to break the bonds. That's why it has a high melting and boiling point. In short, whenever you're breaking the covalent bonds, you need a high melting and boiling point. But when you're just breaking these intermolecular force of attraction, you can go with a low melting and boiling point. Okay, it has a strong, rigid, three-dimensional structure. That's incorrect. Firstly, it's not strong and rigid. Rather, it's a good lubricant. The layers can slide over each other. Option B, it is 4 strong covalent bonds between each carbon atom. That's extremely incorrect. Each carbon atom in graphite is just bonded to 3 other carbon atoms. Okay? In graphite, each carbon atom bonded to 3 other carbon atoms. That's why the 4th unbonded electron in graphite. Because look, this is a carbon atom, okay? In the last shell of carbon atom, you have 1, 2, 3, 4 electrons. So out of these 4 electrons, this 1, 2, 3 electrons are involved in forming covalent bonds, and this 4th unbonded electron in graphite is able to move through the layers of graphite to conduct electricity. So not 4, there should have been 3. Okay, it has layers which can slide over each other. That's correct, as we have seen that these are the layers. This one is the top layer, this one is the bottom layer, and these two layers, because there are weak forces of attraction between them, they can slide over each other. Okay, the D statement is also wrong. It is no delocalized electron. It has this 4th unbonded delocalized electron which can actually conduct electricity. So option C is the correct one. Which row explains the malleability and electrical conductivity in a solid metal? Okay, so what we're dealing with is malleability and conductivity. We know that anything is a conductor because in metals are conductors because of their delocalized electrons. That's what makes them conduct electricity, the conductors. So that's what we're looking for. And the malleability, because look, something is malleable if it can be drawn into sheets. Okay, if it can be drawn into sheets. If you think of metals, you can hammer them into different shapes. You make your car bodies out of metals, you make your gates, your iron bridges, your railings out of metals. How come? Because metals can basically change shape. They can be formed into different shapes. Despite having a high melting and boiling point, despite being strong, having high density, still metals can be molded into different shapes. And that's how they are malleable, because the layers of positive ions, these are the layers of positive ions, okay, in metals. These layers of positive ions can basically slide over each other, making metals very malleable. Okay, malleability, delocalized electron can freely move through the structure. That's correct, but that does not define the malleability. Okay, that's correct, but that's for the electrical conductivity. Rows of positive ions can slide over each other. That's what we're looking for. That's why metals are malleable. These two are correct. Okay, now for electrical conductivity, we're looking for delocalized electrons, and I guess that's the correct one, making option C the correct one. Positive ions can move freely. Okay, one important thing, ions cannot move in metals. What moves is the electrons. Ions stay in place. Okay, question number 10, which says the equation for the decomposition of ammonium carbonate. Okay, let me ask you one thing, a little small thing, but that's going to increase your concept. Why do we have a 2 over here? That's what you learn in class 7, I guess. Why do you have a 2 over here? Because remember, you have a 2 negative over here, a 1 positive over here. That's why you need 2 ammonium to balance out a charge of 2 negative. Okay? So that's one thing. Moving on, the total volume of the gas produced is this. Okay, you are decomposing this compound. You're producing ammonia gas, you're producing carbon dioxide and water. Okay, the most important thing I'd like to tell you guys in a equation, most people think it's the products or the reactants. No, the most important thing is the coefficient. In a moles question, this is like, I guess, the key to everything. 1 mole of ammonium carbonate, okay, 1 mole of ammonium carbonate decomposes to form 2 moles of ammonia gas, 1 mole of carbon dioxide and 1 mole of water. Okay, so that's extremely important, and you're going to see that why have they given us this equation? Because we need to use it to calculate the moles. If we know the moles of one thing, for example, I know the moles of ammonium carbonate, I know that because 1 mole of this forms 1 mole of this, I'm going to know that my carbon dioxide is also going to be formed in 1 mole. Okay, it's 1 mole is going to form it's 1 mole. Okay, so that's the mole ratio. And I also know if I have 1 mole of ammonium carbonate, I'm going to form 1 mole of water. So in this equation, if I know the moles of one thing, I can know the entire moles of everything. Okay, we're given with the MR of ammonium carbonate. The total volume of the gas produced is 360 cm cube at RTP, which mass of ammonium carbonate is decomposed. Okay, so now they have given us the volume of gas, and we know that we are 2 gases forming. One is this ammonia gas and the second is carbon dioxide gas. So let's check out what can we do. One thing I know for sure is my mole ratio and my volume ratio is the same. Okay, you're gonna get it in 1 minute. For instance, देखिए, moles equal to, I know this formula, moles equals to my volume upon 24, because it's cm cube, I'm gonna use 24,000 cm cube. So okay, moles is equals to volume is 360 upon 24,000. So how many moles I get? 360 divided by 24,000, and that's going to give me my 0.015 moles. Okay, now I know that I have 0.015 moles of gases. Now out of these 0.015 moles of my gases, I know that 2 moles is of my this NH3 gas and 1 mole is of my carbon dioxide gas. Okay, so now what I'm gonna do is that I'm gonna simply just do like this, that total moles of gases is 3. Okay, total moles of gases is 3. So look, if 3 on the equation, 2 over here and 1, if 3 moles of gases is basically representing 0.015, so 1 mole over here is gonna represent X. Okay, let me explain it again. I calculated the volume of total of 360 cm cube of the total gases, and my moles came out to be 0.015 moles of 3 gases. Okay, of 3 moles of gases, 2 different gases, 2 moles of this, 1 mole of this. In total I had 3 moles, and 3 moles of gases basically in the equation 3 moles were given with this. So 3 moles basically in the equation represented 0.015 moles in reality. So 1 in the equation would represent X. I hope you get it. So now the value of X is going to come to be, if we divide 0.015 by 3, so I get 0.005 moles. I know that the moles of this thing right over here, that's ammonium carbonate, is going to be 0.005. I have the moles. Now what I need, I have the MR, mass equals to moles times MR. Moles is 0.005 times my MR, which is 96. Okay, one important thing, to do a moles question, you can choose 2-3 different ways. It depends on you, don't worry. If you're doing it with a different way, that's also correct. You should just end up with the same answer at the end. So multiplied by 96, that's going to give me 0.48 grams of mass, which makes option B to be the correct one, 0.48 grams. I hope you understood. Moving on to the next. What is the empirical formula of a compound that contains 3.66 grams of hydrogen, 37.8 grams of phosphorus, and 58.5 grams of oxygen? Okay, now we have to follow an entire method of empirical formula. Okay, that's simple. First we have to write hydrogen ratio, oxygen not oxygen first, I guess we should write phosphorus ratio oxygen. How much percentage we have of hydrogen? That's 3.66. Okay, and for phosphorus it's 37.8, and for oxygen it's 58.5. 58.5. Now the next step is to divide all these percentages by their MR. Okay, not MR, sorry, we're gonna take them as elements. So we're just gonna divide them by their AR, or the relative atomic mass, which you can check out of periodic table. For hydrogen it's 1, for phosphorus it's 31, and for oxygen it's 16. I guess when you have enough of practice of chemistry, you don't need to look at the periodic table for some things because they're so repetitive. Okay, this comes out to be 3.66. Let's do with this 37.8 divided by 31. 37.8 divided by 31, that gives me 1.2. So that's 1.2 ratio 58.5 divided by 16. So 58.5 divided by 16, that gives me 3.656. Okay, 3.656. Now if I round off this everything to one decimal place, this turns out to be 3.6, not 6, it turns out to be 3.7. This turns out to be 1.2, and this 3.7. So these two are technically the same thing. Now the next step is to divide each number by the smallest moles. The smallest moles over here we get is 1.2. So we divide everything by 1.2, and over here the answer is going to be 1 for sure, but 3.7 divided by 1.2, let's check it out. Divided by 1.2, that gives me 3.08. I just take it to one decimal place, which turns out to be 3. So that comes out to be hydrogen ratio phosphorus ratio oxygen, that turns out to be 3 ratio 1 ratio 3. So that means the empirical formula is going to be H3PO3. Okay, H3PO3. Okay, that's going to be H3PO3, this one right here. So that's the empirical formula. Moving on to the next question. I hope you understood the steps. The first was to find the moles. The second was to divide everything by the smallest mole we got, and that's how we get it. Okay, aqueous copper 2 sulfate is electrolyzed using graphite electrodes. Okay, now the most important word I guess in this question is the name of the electrodes, because that tells you either the electrodes are going to react or not. And the solution you have right here is aqueous copper 2 sulfate. Okay, which row identifies the products and observations at each electrode during the electrolysis? Okay, the product at anode and cathode. Okay, let's just do it ourselves. We have aqueous copper 2 sulfate. That means for positive ions we have copper, and negative ions we have sulfate, copper 2 plus sulfate 2 negative. And because we have aqueous copper 2 sulfate, that means we're going to have water ions as well. We have an H plus ion for water, and we have an OH negative ion. Okay, these are the two ions that make up water. Now let's see, out of these two ions, which is going to discharge. What do you guys think? The discharge of ions depends on their reactivity. The least reactive you are, the more you discharge. So between hydrogen and copper, hydrogen is above copper, so hydrogen will not discharge. What's going to discharge is copper. And at the cathode, because at the cathode you have your positive ions. Okay, just remember that cations or the positive ions come at the cathode. So you're gonna have copper, and that can be option A and C. Okay, now moving on to this thing. Sulfate and OH negative ions. Sulfates don't discharge, it's going to be OH negative, and whenever a hydroxide ion discharge, you get your oxygen gas. So it can either be A or D, and that makes A the correct option, because oxygen at the anode and copper at the cathode. So A is the correct option. Moving on, molten sodium chloride is electrolyzed using inert electrodes. Okay, the inert electrodes tells us that electrodes are not going to take part in the reaction, and we have a molten sodium chloride. That means it's not aqueous, we don't have any water, we just have sodium ions and chloride ions. So at the cathode, simply sodium is going to form, and at the anode, simply chlorine is going to form. At anode, negative ion, that's going to be the chloride ion. At cathode, positive ion, that's going to be the sodium ion. The equation for the formation of ammonia is shown. Okay, we're making ammonia, that's through Haber process, I guess. The reaction pathway diagram for the reaction is shown. We have a pathway diagram. What is the enthalpy change for the reaction? Okay, the enthalpy change for the reaction is basically this thing. Okay, first we have to identify either it's exo or endo because they haven't told us. So these are the reactants. Okay, we know that these two are the reactants right here. These two are the reactants, and this right here is the product, and this is the product. Whenever the products are at a lower energy level, reactants are having more energy, then the reaction is exothermic. So this reaction is going to be for sure exothermic. And for an exothermic reaction, the enthalpy change is going to be from the reactants to the products. Though it was written over here, but still it's good. If it wasn't, then you should be able to reduce it. Okay, now this is the enthalpy change. This total line, entire line, is of 3 to 4. You don't take it to be negative or positive, you just say it's 3 to 4, and this one is 250. So out of this entire line, if we subtract this line, we will get this line. So 3 4 2 minus, you can add the minus sign at the end as well, it's completely depending on you, minus 250, you know at the end it's going to be a negative one. So 342 minus 250, 342 minus 250, which gives us a 92. So it's going to be a negative 92. So a negative 92. Why a negative? Because exothermic, and I guess the rest was easy enough. Okay, moving on to the next question, which says that sulfur dioxide, okay, we know it's going to be a simple molecular substance, metal and metal, non-metal and non-metal reacting together to form a covalent bond, is converted to sulfur trioxide. We know it's going to be the contact process. In the contact process, the conditions are 450, 200 kilopascals with vanadium oxide. They've told us everything. Okay, which row describes and explains the effect of changing conditions on the rate. Okay, now many people confuse the rate of the reaction with the equilibrium. Rate and equilibrium are two different things. Okay, so catalyst does not affect the rate, remember this. High pressure, because we're using gases, the rate is going to be higher because the particles have more kinetic energy. Unfortunately, this is correct, but this is not correct, because high pressure does not increase the kinetic energy. What pressure does, it just increases the frequency of collisions, which increases the frequency of effective collisions, and that means that more product is going to be formed because the particles collide more. So this one is incorrect. Catalyst does not affect. Oh, catalyst affects the rate. Oh, sorry, I just confused it. Look, I confused it with equilibrium again. I also confused it with equilibrium for a second. I thought it was equilibrium. Catalyst does not affect the equilibrium, but it affects the rate, and it increases the rate. So right over here, this one is correct. Okay, catalyst affects, and because it's written no catalyst, that means it's going to lower because the activation energy is higher. That's correct. Option A is correct. I'm so sorry for this. Option A is correct. Because a catalyst basically lowers the activation energy, and when you have no catalyst, the rate is going to be lower because the activation is going to be higher because there's no catalyst to lower down the activation energy. And lower pressure, there are more particles per unit volume, there are less particles per unit volume. And lower temperature, the particles collide more frequently. No, the particles collide less frequently because lower temperature means lower kinetic energy of the particles. Okay, hydrogen gas, I just confused it, this catalyst thing, with equilibrium, and that's what I warn you guys the most about. Don't confuse the equilibrium with the rate. I just warned myself right here and then confused it here. So I guess that's a trap everyone can fall into, so be careful. Hydrogen gas reacts with iodine gas to form hydrogen iodide gas in an equilibrium reaction. Okay, now we are dealing with an equilibrium. So now we know it's a reversible reaction. We know that how, if we increase temperature, equilibrium is going to move towards the forward direction because it's endothermic. Okay, what changes increases the yield of HI at equilibrium? Before looking at the yield, everything, I'd like if you guys just know that the forward reaction, because it's plus, it's going to be endo, and the backward reaction is going to be exo. Okay, now all the things that we're using are gases. That means the pressure is going to have, because pressure affects gaseous moles, but it does not affect solid moles. Okay, what changes increase the yield of HI at equilibrium? I know I need more of my HI. Okay, now one thing important over here, look. Over here there's 1 mole of gas and 1 mole of gas. In total we have 2 moles of gases. And over here also we have 2 moles of gases. That means that pressure is going to have no effect. Why? Because equal moles of gases on both sides. Okay, Adding a catalyst. I just told you catalyst does not affect the equilibrium. Okay, so no effect of catalyst. Okay, adding more H plus gas. Okay, if I increase the H plus gas, equilibrium tries to reverse everything I do. Equilibrium tries to, tries to just disobey me and reverse everything that I do. If I try to increase it, equilibrium will want surely to decrease it. And to decrease this, it's going to form more of the product to decrease the H. So more HI is going to be formed. So this one's correct. Okay, increasing the pressure is going to have no effect. Why? Because equal number of moles of gases. Increasing the temperature. Okay, if I increase the temperature, what's going to do equilibrium do? Equilibrium will try to decrease the temperature. And to decrease the temperature, what do? You do the endothermic reaction. So equilibrium is going to do the endothermic reaction. That means it's going to move forward and more of HI is going to be formed, which makes option 4 correct. So it's D, which is 2 and 4. Moving on, the equation for the reaction of carbon with carbon dioxide is shown. Carbon reacting with carbon dioxide to form carbon monoxide. Okay, I'd like to ask you guys one thing. What is happening to this carbon right here? Is it getting oxidized or reduced? I just need to ask you, okay, wow, it's about oxidation reduction. I didn't see this. But still, what is happening to this carbon? From 0, what's happening? From 0 right here, and over here, it's on 4 plus. And over here, the carbon is on 2 plus. How did I know this? It was easy. Look, elemental form, 0. 2 oxygen, that means 1 oxygen had 2 negative. That means 2 oxygen would have 4 negative. To balance out a 4 negative charge, this carbon must have a 4 plus charge. Over here, I have 1 oxygen. That means I have a charge of 2 negative. To balance out this 2 negative, I have a 2 plus on this carbon. Okay, atom that is reduced. What's basically happening? From 0 to 2 plus. That is clear oxidation, an increase in oxidation number. From 4 plus to 2, that's clear reduction. From 4, you're going to 2. So atom that is reduced, this carbon and carbon dioxide is reduced. It is going from 4 plus to 2, which makes option B the correct one. An atom that is reduced, this one is not reduced. This one's oxidized. Okay. Why oxidized? Because it's going from 0 to 2 plus, which is an increase in oxidation number. So that one's be the correct one. Okay, moving on. Aqueous iron 2 sulfate is added to acidified potassium manganate, VII. The purple color of the potassium manganate disappears. Okay, why does the purple color disappear? Because it's turning from purple to colorless. And that's a test for reducing agent. That means that if we have a reducing agent added to potassium manganate, it's going to turn from purple to colorless. Okay, aqueous iron 2 sulfate is for sure a reducing agent, because whenever we add something to potassium manganate and it turns from purple to colorless, that means the thing that we've added is a reducing agent. Okay, the purple color of the potassium manganate disappears. That means iron 2 sulfate is a reducing agent. And potassium dichromate. Okay, we had potassium dichromate. I guess that's another thing. Let's read on. Aqueous potassium iodide is added to acidified potassium dichromate. A dark brown solution forms. Okay, why does this dark brown solution forms? Because iodine gas is released from potassium iodide. Okay, which row identifies the role of iron 2 sulfate and potassium dichromate in these reactions? I guess that's going to be a tricky one for you guys, but you just need to understand that potassium iodide, okay, you're adding dichromate. Dichromate basically turns from orange to green. Okay, that's what it turns into, from orange to green. And what's basically happening is, because you have added potassium iodide basically from Ki, it forms I. Okay, I2. Iodine gas, or no, iodine liquid is being formed, and that is the dark brown solution that's being formed. Okay, so over here you had a negative 1, over here you have a 0. You're going from a negative 1 to a 0. What's that? Is that oxidation or reduction? That is oxidation. So that means that Ki is the, because whenever you are undergoing oxidation, you are the reducing agent. That means Ki is the reducing agent, which tells us that because this is the reducing agent, then the other thing is going to be the oxidizing agent. That means that potassium dichromate has to be the oxidizing agent. And this one right here, iron sulfate, was a reducing agent, which makes option D the correct one. I hope you understood this. This one was a bit trickier than normal, but you just had to learn some color changes. Which row shows the difference between a weak acid and a strong acid? Weak acid is partially dissociated and a strong acid is fully dissociated, so making option D the correct one. Okay, what substance turns methyl orange red? Anything that's going to be acidic is going to turn methyl orange red. So we're looking for an acid. I guess that's going to be option B, the only acid we have here. Which row describes zinc oxide and calcium oxide? Zinc oxide is an amphoteric oxide, calcium oxide is a basic oxide. Amphoteric and basic. You should know that we have two amphoteric oxide in our syllabus, aluminum oxide and zinc oxide. And all the remaining majority, not all, because some beryllium 10, they're all amphoteric, but majority like calcium or sodium oxide, they're going to be basic. Majority metallic oxides are basic, but not all. And the non-metallic oxide, they're going to be acidic. Which row shows the properties of a transition element? Catalyst, yes, I guess that is, good. Red, it's going to be, I guess that's the easiest question in this entire paper. Okay, fluorine is the element at the top of group VII. That means group 7 of the periodic table. Which statement describes fluorine? It's going to be the most reactive, because in group 7, reactivity increases as you go up. It is inert, not at all. Fluorine is like damn reactive. You know that fluorine carbon thing, that Teflon coating you do on your non-stick pans? Teflon, that non-stick coating, that is the fluorine carbon bond. That's so strong that even if you eat it, your body cannot digest it and you're going to pass it out. So that's why Teflon pans, that Teflon coating, that's why pans are coated with it, because even if you eat that Teflon thing, that's not going to harm. It's that much inert, because the bond is so strong it cannot break. It cannot break easily. Acid cannot destroy this bond. This bond cannot be destroyed by anything, like almost not anything. That is the strength of this bond. Okay, it is monatomic, not at all. If it is F2, it is diatomic, it is non-metallic. Yeah, that's correct. It's a solid. No, it's a green gas. Not a green, I guess kind of a yellow gas. Chlorine is a green gas, bromine is a red-brown liquid, and iodine is a grey-black solid at RTP. Okay, when aluminum is placed in dilute HCl, there is no reaction. Why? Because aluminum is covered with Al2O3 on its surface. That makes it inert. This is aluminum. This is your Al2O3 coating. Okay, this one right here is your Al2O3 coating. This coating is extremely inert, and it does not allow anything to reach the surface of aluminum, and that's why aluminum is, it appears as if aluminum is non-reactive because of this green coating that's on its surface. So aluminum is coated with a layer of aluminum oxide. That's why. And zinc is placed in HCl, bubbles of gas immediately are given off. Zinc is less reactive than hydrogen. No, zinc is more reactive, but there is like no coating kind of thing on zinc as much as on aluminum happen. That's why we use aluminum in packing our food and in other things, because though it's extremely reactive, this layer of aluminum oxide, it seems as if aluminum does not react. Okay, which statements about the use of sacrificial protection to prevent iron from rusting are correct? Okay, for sacrificial protection, we use a more reactive metal so that it reacts instead of iron. Okay, because we don't want our iron to react, so we're going to take a metal that reacts instead of iron. Okay, a more reactive metal than iron is used as a sacrificial protector because it undergoes reduction before iron. That's incorrect. Look, metals, if you're using calcium for sacrificial protection, what's going to happen? It's going to go from Ca2+. So metals don't undergo reduction, they undergo oxidation, because from 0 to 2+, that's an increase. So that one's incorrect, and I guess most of you would have thought about it as correct, but this reduction word was confusing. Okay, zinc is used as sacrificial protector because it gains electrons more readily than iron. What do you guys think? Zinc gains electron? Zinc gains electron, really? Zinc is a metal. It has a charge of 2+. 2+ means it loses 2 electrons. It cannot gain. And even if it gains 2, it's not going to get a full outer shell. Why would it do this to itself? Okay, copper is not used as a sacrificial protector because it is less reactive than iron. That's correct. You cannot use a less reactive thing. Magnesium is used as a sacrificial protector because it loses electron. That's correct. More readily than iron. Yeah, these two are correct. So it's going to be option number D, which is 3 and 4. Okay, aluminum is extracted from its ore by electrolysis. What is the role of cryolite in this process? To lower the operating temperature, that's correct. Cryolite decreases, it dissolves aluminum, it increases its conductivity, it lowers the operating temperature because to melt aluminum you need extremely high temperatures. But by adding cryolite, this cryolite thing, the temperatures for melting it is reduced. To lower the boiling point of bauxite, you never want to boil it. Why would you want gas? You're just dealing with liquid. To raise the melting point, you want to not raise, you want to lower the melting point. To act as a catalyst, no. Why would you need a catalyst in electrolysis? Okay, which identifies two greenhouse gases and the three processes by which they contribute to global warming? It's going to be methane and carbon dioxide. So this. Okay, what basically happens is, obviously the first thing is going to be absorption in all of them. Then there is some option. There's creation and reflection, and then there's emission, and then reflection. There's no creation thing, there is emission thing, I guess, because what would you do with creation? That's simple logic. Absorption, okay, it absorbs it, then it emits it, and then reflection of thermal energy, it reflects it back to the earth. So that's what's happening. So making option C the correct one, I guess. So that's going to be C1, because creation has nothing to do with the greenhouse gas effect. Okay, which mixture contains all of the elements in a typical NPK fertilizer? Okay, N stands for your nitrogen, N is for nitrogen, P is for your phosphorus, and K is for your potassium. So ammonium nitrate, okay, and calcium phosphate. Where is our potassium in it? There's calcium phosphate, so incorrect. We need potassium as well. Ammonium phosphate and potassium chloride, that's correct. Because this ammonium thing, what is ammonium? NH4. Ammonium is going to give me my nitrogen, phosphate is going to give me my phosphorus, and this potassium is going to give me my potassium. Okay, potassium nitrate and ammonium chloride, it does not have any phosphorus in it. Potassium carbonate, ammonium nitrate, no phosphorus. I need all three things, so I'm going to go with option B because it has all three. Many people might be confused with this ammonium. They might think that ammonium, it has no nitrates in it, but when you draw the formula, you come to know that it has nitrogen in it. So they might go with option C, thinking it is nitrate, and this option it is nitrate, and this option A that it is nitrate, but you got to realize B is the correct one because ammonium also has nitrogen in it. Okay, bromine reacts with butene. What is the displayed formula of the products of this reaction? Okay, bromine is reacting with butene. That's incorrect. Okay, that's incorrect. We need 2 Br in the center. That's correct. Okay, this is easy peasy lemon squeezy. How guess? Look, butene. What does butene mean? First, you got to understand butene. Look, butene. That means that on your second carbon, you're going to have a double bond. Yeah, 1, 2, 3, and 4 carbon. Okay, and you start your counting from here. This is the first, this is the second carbon. On the second carbon, you have your double bond, which makes it a butene. Now, what's interesting is that in this butene, what's basically going to happen? When you add bromine to it, what's going to happen? It's going to break this double bond, and one bromine is going to add over here, because from where you break double bond, you add the new things, and one bromine is going to add over here. So on the 2 central carbons, you're going to have 2 bromine. That was simply just imagining. How is this possible? Wait a second. If you have a double bond over here, how can one bromine attach here and one bromine attach here? That's completely nonsense. Look, because from where you break double bond, there you have to add your bromine. So one bromine should be attached over here and one bromine over here. So that's the correct one. Over here, this is with butanene. If there was a double bond on the first carbon, then one would attach over here and one over here. Butanene. And this one right here, how is this on earth possible that you have one bromine over here and one bromine over here? This is impossible. How is this impossible? For addition reaction, because you cannot have a double bond between these 2 carbons, the first carbon and the last carbon. Can they have a double bond? Because 2 bromines attach where you break the bond. So how is the bond broken? This can happen by by that substitution thing, that bromine substitutes and then substitutes, but not by addition of bromine. So this one's right here is the correct one. Okay, which statement is correct? Bitumen is used as fuel for ships. No, that's fuel oil. Coal, natural gas, oxygen, all fuels, not oxygen. There should have been coal, natural gas, and crude oil. Okay, hydrogen is the main constant of natural gas, CH4. That's not hydrogen, that's methane. Methane is the main constant. Petroleum is separated into useful fractions by fractional distillation. This one's correct. Use this process to separate petroleum. Which statement explains why ethanoic acid is saturated? Because all the bonds in it are single bonds. Okay, don't confuse it with that saturation. That saturated means that a large amount of solute is dissolved, because when you're dealing with your uh, your organic compounds like ethanoic acid, you think about saturation in terms of bonds, that all bonds are single bonds. Okay, the molecule dissociates, no. There's a carbon oxygen, no. The carbon oxygen double bond, no. The carbon carbon bond. Okay, you might think one thing, that look, there's a carbon oxygen double bond in ethanoic acid, okay, HHHOH. Then why is it saturated? Because saturated means that you should have no double bond. That's incorrect. That's incorrect definition. Saturated means you have no carbon-carbon double bond. There can be a carbon-oxygen double bond, there can be an oxygen-hydrogen double bond, any kind of double bond, but not a carbon-carbon double bond. That is why this compound, despite having this double bond, is saturated, because the carbon-carbon bond is single. Okay? Okay, the carbon-carbon bond in the molecule is a single. That's what you need. You are not looking for though you have a double bond, but still it's saturated because it's not between here. This bond is acceptable, but this one is not acceptable. Okay, which statement about compound in the same homologous series is correct? They have the same chemical properties because they have the same number of carbon atoms. No, they don't. Methane, ethane, propane, butane, heptane, hexane, pentane, all these, they have different number of carbon atoms, okay? Because though they are all in the same homologous series, that the alkane, but they have the same physical properties because they have same number of, okay, they have different chemical properties because they have different number of carbon atoms, they have different physical properties. Okay, the chemical properties basically are similar because they have similar structures, okay? That's why the chemical properties. And the physical properties are different because of the carbon atoms. Because, the physical property, for instance, I tell you about the melting point. What happens to the melting point of ethane with decane? Okay, what happens to the melting point? Ethane has 2 carbon atoms and decane has 10 carbon atoms. What happens to the melting point? What happens to the physical state? Ethane is basically a gas and the melting point is extremely low. Decane is a solid and the melting point is extremely high. What happens? The physical properties, though both belong to alkane series, but the physical properties are changing down the group because your carbon atoms are changing. So the physical properties change because the number of carbon atoms increase or decrease. Okay, which shows the properties of methane? Soluble in water. Alkanes are generally insoluble, so it's going to be a no. State at room temperature, it's going to be a gas because first 3-4 alkenes, they're gases. Gives a positive test with aqueous bromine. It's methane. It's an thing. So obviously not. It's not an alkene. If it was, there's nothing as methane. Remember, methane is not possible. Why it's not possible? Because to form an ene, you need a carbon-carbon double bond. And meth means 1. So between a single carbon, you cannot have a double bond. So, for instance, if you take ethene, it's possible. It's going to have this. And with this thing, your bromine water is going to turn from orange to colorless because you break a double bond. But methane has no double bond. Methane is like this. So no double bond. So bromine water will not turn colorless. So it's going to be option A. Moving on, the table shows 2 methods used to make methanol. Okay, the first method should be your fermentation and second, catalytic addition of steam to ethene. Okay. Which statement gives an advantage of preparing ethanol by fermentation rather than by adding steam to ethene? Okay, we have temperature, we have pressure, we have catalyst, we have source of raw material. Fermentation takes several days to complete. Okay, we need to give an advantage of preparing ethanol by fermentation. So why would we give an disadvantage that it takes several days? Obviously, we're gonna, try to cover us. We are not gonna take this one. We need an advantage. Little energy is used in fermentation. Okay, that's an advantage because look, the temperature over here is only 35, but for catalytic addition of steam to ethene, it needs 300 degrees Celsius. That's a high temperature. This can be thought of. The fermentation of glucose from sugar, cane produces pure ethanol. That's incorrect. It is not pure. That's incorrect. The ethanol is basically mixed with water and then you have to do fractional distillation of that water and ethanol thing produced, and it has aqueous glucose in it as well. So this one's incorrect. The fermentation, it's not pure ethanol. Fermentation uses a non-renewable raw material. That's incorrect. You don't use a non-renewable, you use a renewable, because sugarcane is renewable. So it's gonna be option B, that little energy is used. Because you can grow plants again and again, sugarcane can be grown again, whereas petroleum, once finished, would not come again because it takes millions of years for petroleum to form. So sugarcane is renewable, but petroleum is non-renewable. So this thing uses non-renewable petroleum, but this thing right here uses a renewable sugarcane. So that's an advantage, but over here they just try to trick us by writing non-renewable. Which equation represents an addition reaction? Okay, just by looking at it, I know it's going to be A. Why? Because in addition reaction, you just form a single product, okay? In addition reaction, you form a one product. Over here, two products form. Over here, two products. Over here, three products. So obviously, it's going to be A. That was easy. The structure of part of a polymer is shown, okay? What is this? That's a amide linkage. Then that's an ester linkage. Okay, let's color code the amide and ester linkages. That's going to be a amide linkage. Right here at the center we have an ester linkage. Do we have any other linkages? No. So how many amide linkages? We have two amide linkages and and one ester linkage. One ester linkages, two amide linkages, making option C to be the correct one. Moving on to the next question, which says, which structure represents part of a protein? For a protein, we need amino acids. Okay, I guess it's gonna be this. एक second. Look, that's incorrect. This one right here is an ester linkage. In proteins, you need an amide linkage, something like this. This A is a protein. How come I know? Because right over here, we also have amide linkage, but this one is nylon. And this one right here is a polyester. Okay, the thing you need to understand that you just have to look at the carbon atoms and nitrogen atoms. In a protein, you have this N, C, N, C. So the pattern is N, C, N, C. But in your nylon, you have N, N, C, C. So look, in this nylon thing, N, N, C, C, that's nylon. Okay, and over here you have N, C, N, C. That means that this one's your protein. But to be more specific, you need an amino acid to make a protein. On the amino acid, on one side you have nitrogen and on the other side you have carbon. But for a nylon, you need diamine and dicarboxylic. Both sides N, both sides of this box has C. But over here, one side of the box has N, one side of the box has C. So that's an amino acid. Which piece of apparatus can only measure a single fixed volume? A 250 cm cube beaker, you can measure 100 cm cube in it, because a beaker something like this is gonna have markings on it. Okay, so not this. A burette, no, you can measure 25 as well in 50 cm cube burette, because a burette has multiple readings. It's gonna be a pipette for sure. So it's gonna be a 25 cm cube pipette, because a pipette only has one mark on it. If this is a pipette, this is what a pipette looks like, kind of this. It only has one mark, which is 25. So you can measure nothing apart from this 125 in a pipette. Okay, pure solid copper 2 nitrate can be obtained from a mixture of copper 2 nitrate. Okay, what you're trying to obtain is a solid and a pure solid. A mixture of copper 2 nitrate and copper powder. Okay, 3 stages in the methods are listed. Add water and stir, crystallize and filter. After the 3 stages, the copper 2 nitrate is washed and dried. What is the correct order of stages X, Y, Z to obtain pure solid copper 2 nitrate from the mixture? Okay, you know that you have a mixture of copper nitrate and copper powder. Copper powder is going to be insoluble, so first you add water and you stir. Okay, so first is going to be X, you add water and stir. The second thing that you're going to do is the copper nitrate is then washed. Okay, the second thing that you are going to do is you're going to filter out the copper powder. Okay, you have this beaker. What you do is first you add water and stir. Then you filter out the copper powder on this thing. Now what is left as a filtrate is your copper nitrate. So you crystallize it, and after crystallizing you wash and dry the crystals. So it's going to be X, then it's going to be Y, and then it's going to be Z. So it's written in correct order. This one's going to be the first one, this one's going to be the second, and this one's going to be the no, sorry, this one was the first, this one was the second, so sorry, not this. I just said it correct, but I circled wrong, like this, sorry. Number one, then filter out the copper and then crystallize it. So it's going to be X, Z, and Y. Moving on to the last question of this sheet, which says, which row describes the test and observation for aqueous sulfate ions? So if you guys haven't learned the test, kindly do them. So you're going to just add nitric acid, then you're going to add barium nitrate and white precipitates form. I guess that's option B, which gives us the test for our sulfate ions. And with that, the video ends. And thanks for watching.